Hi, Becky. Hi, Ethan. Hello, Attune. Thank you. It came a couple days early. I thought I was only gonna be able to use it next week, but got this great thing. I might order a second one because I can't really go side to side. You know what I mean? And I really liked having two papers side to side. So I might order a second one. But they are a little expensive, so I'm still thinking about it. All right. So it looks like it's 10 o'clock. We have 5 more minutes. Go ahead, get some water. All right. Make yourself comfortable. Take out your notes. Let's get pumped. Okay. I'm gonna get some water myself. Thanks, Itamar. Looks like we got 15 people. Cool. Good morning, Saeed. Are you vibing right now? Excellent. That's great to hear, Saeed. Two more minutes, okay? Oh, I need to hook my computer to a charger. Hold up. Okay. Good morning, Jacqueline. All right, it's 10:05. We only have 21 out of 33 students. It's around 66%. That's totally cool. Hopefully they can join us later. And if not, and they're just planning on looking at the video later, that's cool too. All right, so let's start. Today, we're going to go over a concept called electric potential. So in your notes, please take the time to draw this grid out. It's a 5x5 grid, right? So this is very similar to electric field. We're just going to be looking at what happens at this point in space, at this point in space, at this point in space. And obviously this is a two-dimensional view of space, right? If we really wanted to examine like real life space, we would try and like make like a 5x5x5 cube. All right, how much space should it take up on your page? Probably like half, half of a good amount, Ethan. Yeah, so instead of a 5x5x5 cube to look at, what happens at this point, and 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 all the points in space all around, okay, we're just going to be looking at a 2D slice, right? So this is 2D space, all right? So and I am going to write down a couple values here. I'm going to write here, it's going to be 7, and this will be joules per coulomb. All right, J over C. Okay, this will be 7 joules per coulomb again. This will also be 7 joules per coulomb. This will be 6 joules per coulomb, 6 joules per coulomb, 6 joules per coulomb. And why don't here we also make it 6 and 6. All right. The units are important, but if you're gonna get tired of just drawing 25 J over C's, then you can omit them. I'm just writing them because I like to. All right. So this is 5 joules per coulomb, 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 5 joules per coulomb here too. And I'm going to go back up to 6 joules per coulomb here, 6 joules per coulomb. And I'll put another 5 joules per coulomb here. Here will be 4 joules per coulomb, 4 joules per coulomb, 4 joules per coulomb, 4 joules per coulomb. Here we'll have 3. And here we'll have 2. Right. Hopefully we can all read these numbers, right? Let me know if you can't read the numbers, okay? Cameron, do you prefer Zoom? We can talk about this later, okay? I think the big advantage of streaming like this is that if you miss it live, you can look at it later. And I think Zoom, because it incorporates the video from multiple channels, the quality here is not going to be as good, so you might not be able to read everything. As much as I would like to see your face, Cameron. Okay? All right. So you'll notice that this is not in newtons per coulomb. All right? So what that means is every point in space here, these values I've given you, it is not electric field. It is it's a second type of property of space. I can say objects can have internal properties, right? So an object can have mass, an object can have charge, like electric charge, and an object can have like size, right? It can like be as large or as small as I make it, as long or tall or as wide as I make it. Points in space actually have things about them too, right? And one of the things we learned is electric field, right? A point in space can have an electric field, and a point in space here can have something we call electric potential. Okay, so I'm going to try and write a little better. Yeah, I'll write less crooked in the future. But I'm like on the floor right now. I gotta really work this out. So this is the second. It's the second property a point in space can have. So if I'm looking at, oh, this point in space, like 1, 2, 4, right? 1, 2, 4. And I'm looking at this point. I'm looking at this point in space. I can ask, hey, what's the electric field at that point? And I can also ask, what's the electric potential at that point? There are two different things. The one thing that makes electric potential a lot easier to understand than electric field is that it's not a vector. It's a pure scalar, right? So I can say, oh, what's the electric potential at that point? 4 joules per coulomb. That's it, all right? What's the electric potential out there? 6 joules per coulomb. That's it, right? I don't have to worry about where it points or anything like that. It's just there. It's just this value of electric potential. And electric potential is not electric potential energy, all right? So that's really key. Now, the really cool thing about electric potential is that if an object is right there, right, I would say, what is its value of electric potential? It's 6 joules per coulomb. But I don't really care about that, right? This is a real contrast to electric field. Like, if I say, oh, my electric field there is 6 newtons per coulomb, that's a really real thing. That means if I place a 2 coulomb charge there, it'll experience a 12 Newton force at that point. Now, if I place a 2 coulomb charge here, where the electric potential, not the electric field, is 6 joules per coulomb, it doesn't do anything yet. I don't care about electric potential. What I really care about is change in electric potential, all right? So if I have a particle and it starts here, okay, and then it moves here, all right, then its electric potential has changed, right? Because the object itself has moved from an area of 6 joules per coulomb, and it's moved to an area that has 3 joules per coulomb. So what we say in this example, right, and you should have that drawn in your notes, right, an object going from a region with 6 joules per coulomb to a region with 3 joules per coulomb, all right? What we say there is the change in potential, and we abbreviate electric potential with the letter V. Okay. Again, I'm really sorry about the abbreviations. I know they don't make a terrible amount of sense. Okay. So the electric potential V, and for this particle, right, that went from 6 to 3, I would say, hey, it's change in V, and that's what I really care about, right? I don't really care about, oh, what's my potential at this point? What's my potential at this point? I don't really care. I really care about the before and the after, right? So V, the change in V, we would say was 3 joules per coulomb, all right? Or was it? Or was it? If I started at 6 and I ended up at 3, would I say my change is 3? Or isn't my change -3, right? It should be -3, right? Because it's 3 minus 6, right? Final minus initial, so it should be -6, -3, right? So my change in voltage, my change in electric potential was -3 joules per coulomb, okay? And we use this in a very similar way to electric field, right? So I would say electric potential, what is it related to? Well, just like the name implies, it's related to potential energy, but it is not equal to potential energy, okay? The formula we're going to look at is change in electric potential energy is equal to the charge times the change in potential that it experiences, okay? That's your biggest formula you gotta know. Other textbooks write this as work. The work done by the electric force or the electric field is Q times delta V. That's because the work is gonna equal the change in electric potential energy. So Itamar had a really great question. He said, I'm confused. I mean, I'm sure you guys can all read this question. Is space just a mesh of all these different properties, like space itself is defined by electric potential, electric field, etc., or is it its own thing and just has these properties? I would go with the latter explanation, all right, that you suggested, that space indeed is like just empty. It's just something where something can occupy some space, right? So like, how do I define space? Whoa. So that's a weird question. What I'm saying is space is just empty space. That's what it is, right? It's just a point that can have something in it, like a particle can occupy this point in space. But that point in space can also house other things other than objects, right? It can hold values of electric field, it can hold values of electric potential, and it can also hold values of gravitational field and gravitational potential, all right? But we're only going over electric potential right now, all right? And these values that it has, the points in space, if a point has a value of electric field, then what that really does is it affects how it affects the particle that occupies that space. So if a point in space has a value of electric field, that means when I place an object in it, finally, like what's the purpose of space? It's to put objects in it, I guess. So when I finally do place an object in that field, in that space, it has the potential to have an electric force acting on it as long as it's charged, right? That's what it means. So like if particle A occupies a point in space, like, oh, it's just sitting there. A lot of things can happen to that particle while it's in that point in space, depending on the values of the fields and the potentials at that single point. So is the space between electron shells not space? Okay, so here's the other weird thing we're doing, Itamar, in that here we're looking at quantized space. We're looking at, oh, what's it at this point, this point, this point, this point, where in classical physics, a lot of people describe space as continuous, right? So that means in addition to these 2 points, there's that point, and then there's that point, and that point, and that point, and that point. Like, how do I represent this area by the entire collection of points that it comprises? You kind of can't, because there's an infinite amount of points in a continuum. Okay, so there aren't 25 points in space here. There is an infinite amount of points, but we're just choosing to look at these 25 because I just want like a good picture of, what's going on here. Okay, all right. So back to where we were. We're with electric potential. All right, so let's pretend this object that lost 3 joules per coulomb, let's pretend it was 2 coulombs. Let's pretend that this object that moved before, after, let's say, what if it was positive 2 coulombs? What changes? Okay, so before we move to this problem, this is the crux of the lesson today. All right, I just want to make sure I answer all the questions, so thank you very much for asking. Maya asks, hi Maya, what changes electric potential besides charge? I'm not really sure I understand your question, because for this map that we've created, this region of space that has all these values of electric potential, I never told you where it came from, right? These values of potential just exist. Now, it's true that they exist and they fluctuate because of some charged objects nearby and stuff, but I'm not asking you to think about the source of the potential. I'm just telling you that, boom, here are my potential values, okay? Like, Maya, like, right now we're examining what happens when a 2 coulomb charge moves from here to here. Right after that, we're going to look at what happens when a 4 coulomb charge goes from there to there. And it doesn't matter if I move a 2 coulomb charge here and a 4 coulomb charge here. It's not going to affect this external potential, okay? Jacqueline asks, does an object have to be charged to have electric potential? All right, let me make this really clear. Objects do not have electric potential. This is not a 7 joules per coulomb object. This is not a 7 joule per coulomb object. This is not a 6 joule per coulomb object. What I'm saying is this is a point in space, and the electric potential value here is 6. This is a point in space, and its electric potential value is 4. I can place an object at that point, and that object will feel the potential at that point is 4. And if I place an object there, the object will feel that the potential there is 6. And if I move an object from here to here, no matter what its charge is, no matter what its mass is, that object will perceive a change in electric potential of negative 3 joules per coulomb. All right. Oh, thank you, Sarah. I'm so glad I got to answer your question. Ethan Yen, the point in space, I think, yeah, the points have the potential. Objects do not have potential, all right? Objects can experience the potential by actually existing at the point that has the potential, okay? Thank you, Jacqueline. So good to see you. Maybe I will do a Zoom just so I can see your faces, because this whole one-way thing is kind of weirding me out. Anyways, so where does the potential come from then? It comes from other charges that is not this charge, right? So maybe there's a charge here and a charge here, and that's what's giving these potential values. Very much like electric field. Like, where does the electric field come from when an object experiences the electric field? It comes from other charged objects nearby, okay? Okay. So, if this charge was positive 2 coulombs, I would say, according to my formula, its change in electric potential energy was negative 6 joules, right? I would say it lost 6 joules of potential energy, okay? If it was positive 4 coulombs, right? Didn't change the mass, right? I just added like a bunch of protons, no big deal, all right? So for the positive 4 Coulomb object, the change in electric potential energy is negative 12 joules, right? Notice that when I change the charge from 2 to 4, I'm not changing the value of electric potential, right? I'm just changing the charge of the object that experiences the change in potential. No, a joule per coulomb is equal to a volt, okay? But the reason why I don't like using volts and I really like using joules per coulomb is because a volt is the unit with which we measure potential. And potential is abbreviated by V. So I don't want to write delta V is negative 3V. You know what I mean? Then like, which V is the V? So I'd rather write delta V equals negative 3 joules per coulomb, all right? If you start getting lazy, you can write like change in potential is negative 3 volts, but I would prefer you then to write out volts instead of V, because then you have delta V equals something V, and that's weird, okay? Great questions. Keep them coming, okay? Please. I'm going crazy here alone in my apartment, okay? So, boom. I have this object, and it has experienced a drop in potential energy, right? So another analogy I can write before we move on is force is to electric field as change in electric potential energy is to change in voltage, right? You can, for the time being, you don't have to think of what field is as a real thing. You don't have to think about what voltage is, what potential is as a real thing, because it's invisible, right? Like, how can I just like look at this point in space and tell you what the electric field is, what the electric potential is? I can't. It's invisible. I can't taste it. I can't smell it. You know, I just gotta like take it for granted that the potential at these points is exactly what I'm telling you, right? You just gotta like slurp that up. I'm sorry, right? But so while it's really hard to imagine what these quantities are like physically, right? Because you can't really touch them, you can think of them as tools, right? They're both hypotheticals, right? What is the electric field really? It tells you what the force on a charged object would be if I knew its charge, right? Because force is just Q times Z. So the unit of E is newtons per coulomb. It's literally telling you how many newtons of force you would experience if I knew the charge in coulombs, right? It's newtons per coulomb, okay? Now, this is the exact same thing. What is potential difference? What is electric potential? Don't worry about what it is, right? All it is it's a tool that'll let you know how much energy I gain or lose once I know the charge, right? Because change in electric potential energy is just Q times delta V, right? So, if it was 5 coulombs, then I would lose 15 joules. If it was 10 coulombs, I would lose 30 joules, right? It's a hypothetical change of energy per unit charge. Just like how field is a hypothetical force per unit charge, okay? No. Ethan, electric potential is not electric potential energy. All right, look at this. This is change in electric potential energy is equal to charge times change in potential. Potential is measured in joules per coulomb. Potential energy is measured in joules. So because this is a coulomb times a joule per coulomb, you get a joule, okay? That's the biggest hiccup for this unit, is mixing up potential energy and electric potential. They are not the same thing, okay? Change in electric potential will tell you how much energy you lose as long as you know the charge. Just like how a field will tell you how much force you experience as long as you know the charge. Okay? I can take a really quick break now to take some questions. All right? Ayanava, where did the change of energy go if it is conserved? That's exactly what we're going to answer next. Great question. Okay? No, Ethan, I multiplied 2 coulombs by the change in potential, not potential energy. Okay? My potential here is 6 joules per coulomb. My electric potential here is 3 joules per coulomb. So my change in potential is -3 joules per coulomb. So I multiply -3 joules per coulomb by 2 coulombs, and I get 6 joules. All right, Ethan, delta V is not potential energy. It's potential. When I multiply charge by potential, I get potential energy. Yes, Ethan, you have to realize change in potential, the potential is not potential energy. They're two completely different things with very similar names. Yeah, change in potential is delta V. What? Isn't change in potential delta V? Yes, it is. Change in potential, -3 joules per coulomb, is delta V. And then I write delta UE. These are not equal. Delta UE is change in potential times the charge. Okay? All right, if those are the only questions, we're going to move on. Ayanava asked a great question. Okay? Chris says, so is a negative electric potential moving away from a... No, I don't want to think about that. Again, you never think about negative potential or positive potential, because yeah, it is possible to have a point with like -4 volts, joules per coulomb, -8 joules per coulomb, but what I really care about is the change, Chris. If I'm at a point in space and I have a potential value of 7 joules per coulomb or -7 joules per coulomb, I don't care. That doesn't tell me anything. I don't know anything until I move and my potential value changes. All right, I don't care what the potential is at that very instant. I care about the change in potential when I move from point A to point B. All right, so I don't care if I have negative potential or positive potential. What I care is, do I have a gain in potential or a drop in potential? You wrote at the bottom half of the page. Oh, that's not multiplication, all right? Thank you for clarifying that, Ethan. Right? So I'm saying if it was 2 coulombs, what's my change in potential energy? 6 joules. If it was 4 coulombs, let's look at if it were 4 coulombs, then my change in potential energy is -12 joules. Yeah. Okay, excellent, Ethan. Thank you so much. So the electric potential energy is for the object in space. Yes, right? And it's going to change. It can lose 6 joules, it can lose 12 joules. I don't know how much it loses until I know the charge, right? Until I know the charge. So let's pretend it was, I don't know, 3 coulombs. Let's pretend the object in question is 3 coulombs. Okay. Okay, so if the object was positive 3 coulombs, then the change in potential energy was equal to Q times delta V, and this is 3 coulombs times negative 3 joules per coulomb. So did it gain or lose potential energy? It lost 9 joules of potential energy because the change was negative. Okay. Now, if it was a negative 3 coulomb object, then it would have gained 9 joules of potential energy. Okay? And Jacqueline, you just answered Ayanava's question. What the heck do you think happens when my object moves from here to here and it lost potential energy? That whole time it was speeding up. It was like rolling down a hill, and it gained kinetic energy. All right. Because I have U plus K equals U plus K, right? Was there any heat created? I don't think so. This object is just in space, outer space, in a vacuum, no friction, no collisions. So when I lost my potential energy, the only energy I really could have gained was kinetic. So there was acceleration, indeed, Diman. The really cool thing about the analogy we're about to pop up on is that I just need to sit down for a second. I've been bending over a lot. Nice. Okay. Oh, this is really comfortable. If it gains potential, it would decelerate. Yes, Sarah. And eventually, it would reach a point where the velocity would be 0, and you couldn't go any further, right? I'm going to draw this really quickly. All right. What is this? You're cool, Cameron. I miss you guys, okay? I'm going to write 7, 6, 5, 6, 4, 3, 2. Can anyone guess what this is? What have I just drawn here? 7, 6, 5, 4, 3, 2. And there's like 6 here too as well. Anyone in the chat like to take a guess about what this is? It's related to the very first thing you drew. Diman, these are not field lines. Yes, this is an alternative way to represent potential in 2D space. This is electric potential, but drawn almost like a topographic map, right? Except instead of elevation, these lines represent potential values, right? So if you look at the very first thing that we drew, it's the same thing. I have a region of 7, 6, 5, goes back to 6, 4, 3, 2. Okay? Why is that important? Because this is a much quicker way of drawing this, and it basically tells the same information. And not only that, like it says, hey, what if I move a particle from here all the way to here? How much does its potential energy change? 0, because its change in potential was also 0. So our particle, what did it do? We moved it from here all the way to here, right? That's all we did. It went from 6 joules to 3 joules. 6 joules per coulomb to 3 joules per coulomb. And it lost 3 joules per coulomb. And because it was positive 3 coulombs, it lost 9 joules. All right? I really like this analogy because it ties in perfectly to gravitational potential, right? If this instead was elevation, and I would say, oh, how much height did it lose? How much potential energy did it lose? How much kinetic energy did it gain? Because it went downhill, right? This is the exact same thing, right? So I lost 9 joules of potential energy. What happens when I go downhill? I gained kinetic energy. Is the space in between also good? Sure, Chris, but it's just here, it's like 5.5. I just don't know, right? So if you really wanted to do this, you would need with some amount of precision, I would have to add extra lines, right? 5.5, 4.5, and maybe 5 is also here. And this is 4.5, and this is 6.5. It's just you'd have to do it everywhere, right? And some topographic maps really do have a bunch of lines. If you Google image complicated topographic map, you're going to end up looking at a lot of cool things. Okay, how would this be related to the electric field? Can you overlap the electric field with electric potential? That's the last thing I'll leave you with today. So first I'll answer Dimon's question, but secondly, I want to go over the types of problems that you're going to experience, all right? I'm going to give you a problem like this, and I'm going to ask for, hey, if that object here's your first homework problem, okay? It's just related to this. If this object, I move from here to here, if it were a proton and it started from rest, all right, and don't worry, I'm going to write this out and email it out today by 1 o'clock. I didn't email you this sheet last night because I didn't know what exactly I wanted to cover today or how far we would get. So now that I know, here we go. Here's your first problem, and I think I'll only add a second problem to the practice. So the first problem is, if I'm a proton and I start from rest here, how fast am I at that point, by the time I reach that point? There's your first problem, okay? It's literally just conservation of energy, but you're going to have to look up some information on the internet, like what's the mass of a proton, what's the charge of a proton, etc., etc., etc. Okay? All right, so let's move on. Oh, buddy. Okay. Dimon, you can map electric field with electric potential. The electric field always points perpendicular to the field line, the potential lines. Oh, these are called equipotential lines. They're exactly what they sound like. Along that line, the electric potential is equal. It's always the same, right? So along this equipotential, my potential is always 6 joules per coulomb. Along this equipotential, my potential is always 5 joules per coulomb. Here, I'm always 3 joules per coulomb, right? And the electric field actually always points perpendicular to the equipotential lines. So what's my electric field at that point? It points here. What's my electric field here? It points there. What's my electric field here? It points there. What's my electric field here? It points there. And they always point downhill. Because literally it's telling you where a charged object would go, and it wants to go downhill, right? And it'll go in the steepest direction, blah. Okay. All right, I think that's it. This was a nice, I think 35, 40-minute stream. Okay. Does anyone else have any other questions? All right, then I'll leave you with this assignment. Thank you guys for the 4 likes. It really helps out the channel. Make sure to hit subscribe. Smash that like button. And I think that's all YouTubers say, right? That's like all they ask you to do. Do they ask anything else besides subscribe and hit the like? Leave a comment. And I see a lot of you have already done the chat, so I really like you. How should we be submitting all the homework? All right, so that's a really good question. I'm gonna be doing something a little different. So this week's like our little pilot test week, right? Thanks, Maya. Bell button. What's the bell? Oh, turn on notification. Yeah, cool. Turn on notifications. Thank you. You guys know how much YouTube I watch now, I guess. Oh, this video was sponsored by Isopropyl generic brand alcohol. Make sure to rub down all surfaces you touch and before you touch them, and stay safe. Okay. What was I gonna say? Today's a pilot week. I'm going to just fulfill my promise and like keep the format as I did. But I think starting next week, here's how it's gonna go. So Monday we'll have a lesson, and then by Monday night, I want you to submit any work or any quest, like a picture of your work or picture of your questions regarding the work. If it's confusing, that'll just count as your homework grade. You don't even have to complete the worksheets, right? You just got to like try, and for every problem you can't complete, I want you just to ask a question about, like write down like, oh, I don't get this, like how do I do this, like is this right? And then on Tuesday, I will go over the solutions. And based on the responses I get, I'll answer like some common theme questions. Okay? And the pattern will repeat. Wednesday night, Wednesday night, your responses for the practice will be due. Thursday, we will go over it on the doc cam. I ordered a new doc cam. It's coming in the mail. Get excited, okay? And I'll answer any questions there. And then Friday, we'll have a more informal, like maybe Zoom so I can see your faces. We'll just do something fun, right? I'll give you some music to listen to. I can show you some cool recipes I've been experimenting with. Who knows, right? But it's so now instead of Monday, Tuesday, and then Friday we go over the answers, it's going to be Monday, turn in your responses, go over the responses Tuesday, Wednesday, turn in your responses, go over the responses Thursday, and Friday we'll have like a more fun kind of stream. And I think that's about it. You also do have an additional assignment due today. It's just finding a partner, because I think this isolation can be really draining for a lot of us. So I want everyone to find at least one partner. I'm going to create an assignment. All you got to do to turn that in is just type up the name of your partner, parenthesis S. You can get in the groups of up to 4, okay? And just tell me who you're working with for like the remainder of the school year, because there's a good chance we're not going to see each other again, all right? All right, so that's the end of my stream. Yeah, expect the worksheet around 1 o'clock, because I have to stream with my Regent students from now until noon. So right after noon, I'm gonna try and do that for you. Tomorrow and Thursday, tomorrow you are going to, let's see. You're gonna turn in that first assignment I'm giving today about finding a partner. That's what's happening tomorrow. Thursday, I'll have open office hours. All right, maybe that'll be on Zoom. I'm still working out the best way to do that. And Friday, we're going over answers. every sheet, including the one I'm sending out today, both the sheets. So both the sheets, the one I sent Sunday and the one I'm sending today, is due Friday. You don't, yeah, and I guess Thursday night you can submit a picture of your work. I'll create an assignment on Google Classroom for which to do. Beautiful outside. I'd recommend taking a walk as long as you don't really go near anybody, okay? Stay safe. I miss you guys. And yeah, bye. Only 17 likes?